Thank you for joining me today. Welcome to another presentation in Chem Safety's online webinar series. Today, we're going to look at managing welding and metal fume exposure in the workplace. My name is Paul Robertson and I will be your presenter today. Please feel free to send any questions regarding the webinar or welding and metal fumes through to info@chemsafety.co.nz. Our details will be on the follow-up email, which will also include a link to the recording of today's session. So just a quick run through of the topics that we will discuss today. We'll firstly look at the chemical properties and composition of welding fume. Then we'll look at health effects of welding and metal fume exposure to see why we need to protect ourselves. We'll look at how metal fume can enter the body and move on to common types of welding used in the workplace and their implications on fume composition. I'll also talk about options for controlling welding fume exposure in the workplace, and then I'll talk about workplace exposure standards and workplace monitoring for welding fume. So what are welding and metal fumes? Welding's a process that's used to join materials, typically metals, by melting the workpieces and often adding a filler material to form a strong bond between them. Welding fumes are complex mixtures of various particles and gases produced during the welding process. These fumes are generated when metals and other materials used in the welding are heated to high temperatures, causing them to vaporize and then condense into tiny particles. Particles generated during welding and thermal cutting are very small. In general, they have a diameter of less than 1 micrometer. In most cases, they can be less than 0.1 micrometers, and they are termed ultra-fine particles. This makes them respirable and called welding fume. The particles are typically very small, which means they can penetrate deep into the lungs. While all welding and thermal cutting processes generate fume, the plume may not be visible to the welder. Many metals react quickly with oxygen and air to form oxides. Common metal oxides in welding fumes include iron oxide, zinc oxide, and manganese oxide. The types of metals and the severity of the health effects they can cause is dependent on the type of welding and the metals being welded, and any coatings or contaminants that may be on the metal. Common gases produced during welding include ozone, which is produced especially during processes like gas metal arc welding, where intense UV light can generate ozone. Carbon monoxide that can be formed from incomplete combustion of hydrocarbons or from the reaction of carbon with oxygen. Carbon dioxide, often used as a shielding gas in welding processes and also produced as a byproduct. Nitrogen oxides from the heating of atmospheric oxygen and nitrogen can also be produced at high temperatures. And there's also several chemical compounds that can be produced, one of which is fluorides. These can be found in some of the fluxes and coatings around welding, and hydrogen chloride can be released from certain fluxes or coatings containing chlorine. So, different welding processes produce varying amounts of and types of fumes, but some welding methods are particularly known for generating higher volumes of fumes. Arc welding types in order of decreasing fume production include flux core arc welding processes, shielded metal arc welding or stick welding, then gas metal arc welding or MIG welding, and tungsten inert gas or TIG welding is generally recognized as producing lower levels of fume among the common welding types. It should also be noted many other metal cutting processes such as plasma cutting and arc gouging or cutting will produce metal fumes. The type of metal being worked on will also affect the composition of welding fume. You can see the difference in fume composition between mild steel and stainless steel on the right-hand side of the slide. So in stainless steel, there are large components of nickel and chromium in the fume. Let's move on to health effects to understand how exposure to metal fumes affect the human body. Welders are potentially exposed to metal fume and gases, ultraviolet radiation, noise, electric shock, burns, and other hazards. A worker is 15 times more likely to die from a work-related disease than from a work-related acute injury. Therefore, the importance of protecting workers against fumes from welding is critical. Welding and hot cutting produce metal and fluxing fumes made up of toxic gases and very fine particles. Inhaling welding fumes can cause ill health and workplace disease. Acute bronchitis is a short-term inflammation of the large and medium-sized airways of the lungs. Symptoms include chest discomfort, wheezing, coughing up mucus, and shortness of breath. Ozone gas produced during plasma arc, metal inert gas, and tungsten inert gas welding processes can cause blood and fluid to build up in the lungs. Occupational asthma is commonly associated with exposure to stainless steel fumes. Stainless steel fume contains chromium oxide and nickel oxide, which cause asthma. Symptoms include chest tightness, wheezing, and shortness of breath. Metal fume fever is caused by inhaling metal oxides from galvanized welding. Exposure to metal fumes such as zinc, magnesium, and copper can cause metal fume fever. The symptoms are similar to the flu and often worse at the start of the week and weakest after a couple of days off. Effects usually aren't long-lasting for metal fume fever. Pneumonitis is inflammation of the lung tissue, which can lead to severe and sometimes fatal pneumonia. Chronic long-term health effects include chronic obstructive pulmonary disease, COPD, which includes chronic bronchitis and emphysema. COPD causes permanent lung damage. Symptoms include difficulty breathing, coughing, mucus and chest tightness. Damage happens gradually over a long period of time, so regular health monitoring is important to detect changes. Welding fume has been linked to multiple forms of cancer. It is classified as a carcinogen by International Agency of Research on Cancer, or IARC. Cancers in the lung, larynx, and urinary tract have been linked to exposure to welding fumes. Pneumoconiosis is also a restrictive lung disease caused by ongoing exposure to fumes from aluminium and arc welding. So other health and safety risks from welding include arc eye. This is an injury to the front of the eye, the cornea, caused by exposure to radiation generated by welding. Burns may be due to fire, explosion, or electric shock, or even UV radiation generated during welding. Electric shock, the welding process uses electrical arcs and electrical equipment. Heat stress and heat exhaustion. Working in extreme heat indoors or where there's high humidity or radiant heat being generated, or outdoors can cause serious illness or injury. Neurological damage. Some studies suggest exposure to manganese present in mild steel welding fume may lead to neurological symptoms similar to Parkinson's disease. Damaged hearing or hearing loss. Welders often work in noisy environments and carry out noisy operations such as needle scaling and grinding. Ocular melanoma. This is a rare eye cancer that may be associated with welding, particularly the intense flame and arc emitted by UV radiation. Skin damage. This includes allergic contact dermatitis from materials containing chromium. Suffocation. Welders working in confined spaces are at risk of suffocating due to lack of oxygen or asphyxiation. During welding, oxygen in the atmosphere is burnt or displaced by other gases such as argon, helium, and nitrogen, argon-based mixtures and carbon dioxide, or the introduction or buildup of carbon monoxide from combustion engines nearby. Common hazards are trips, slips, and falls, and they're also susceptible to vibration-induced pain and disorders. Workers carrying out needle scaling and grinding may be at risk from harmful levels of vibration, which can cause painful and disabling disorders of the blood vessels, nerves, and joints. The main exposure route to welding fume is via inhalation, although the skin and eyes can be target organs. Metal fumes are inhaled and can deposit in different parts of the respiratory tract, depending on their size. Larger particles tend to be trapped in the upper respiratory tract, which consists of the nose and throat, while smaller particles can reach the lower respiratory tract, which consists of the trachea, bronchi, and alveoli. The body's first response is often irritation of the mucous membranes lining the respiratory tract. This can lead to coughing, throat irritation, and shortness of breath. The body recognizes metal fumes as foreign particles, triggering an inflammatory response. White blood cells and other immune cells are mobilized to the site of exposure to remove or neutralize the particles. Inflammatory cytokines are released to mediate the immune response, which can lead to symptoms like fever and systemic inflammation. Metal fume fever is caused by this immune response and can develop a few hours after exposure. This typically resolves within 24 to 48 hours after exposure ends. Metal fumes can generate free radicals and reactive oxygen species within the body. These highly reactive molecules can cause oxidative stress, damaging cells and tissues, particularly in the lungs. Chronic respiratory conditions are caused by long-term exposure to metal fumes. Chronic bronchitis and asthma are two of these conditions. It can also contribute to the development of more serious conditions like pneumoconiosis or interstitial lung disease. Systemic toxicity. Certain metals like cadmium and lead can accumulate in the body and cause systemic toxicity, affecting various organs such as the kidneys, liver, and bones. Chronic exposure can lead to conditions like cadmium poisoning or lead poisoning. For cellular repair, the body attempts to repair damage through cellular regeneration or repair processes. The effectiveness of these mechanisms can vary depending on the level and duration of exposure. Most elimination of metals from the body is via urine and sweat. So hexavalent chromium is a significant health risk, so we'll discuss it briefly now. Chromium metal is added to alloy steel, particularly stainless steel, to increase hardenability and corrosion resistance. A major source of worker exposure to chromium-6 occurs during hot work, such as welding on stainless steel and other alloy steels containing chromium metal. Hexavalent chromium is one of the valence states, +6 of the metal element chromium. Chromium-6 is known to cause cancer, including lung cancer. In addition, it targets the respiratory system, kidneys, liver, skin, and eyes to cause irritation and disease. Chromium-6 is a respiratory and skin sensitizer, which means a sensitivity can be developed through repeated or high exposure. When a sensitivity is developed, small amounts of exposure can trigger occupational asthma and or skin reactions. You'll see later that hexavalent chromium has been assigned a very low workplace exposure standard. Therefore, control of this substance is critical to protecting worker health. Chromium-6 compounds may be used as pigments in dyes, paints, inks, and plastics. It may also be used as an anti-corrosive agent added to paints, primers, and other surface coatings. So it's important to be aware of what's coating the metals being welded. So let's take a look at the hazard hierarchy of controls so that we can see the order of most effective controls for controlling welding fume. First, try to eliminate the risk. If this is reasonably practicable, this can be done by removing the source or cause of harm. If elimination can't be achieved, then try to minimize the risk. Substitution. Can a less hazardous form of welding be used? Isolation. Can we isolate the task so that less people are exposed? For example, use of welding bays and welding screens protect other workers from welding flash, and design of fume-controlled work areas decrease the amount of people that are exposed to welding fume. The types of engineering controls available include local exhaust ventilation or LEV, fume extraction systems, capture hoods, and ducting. Dilution ventilation. General air movement and ventilation strategies exist to remove contaminated air from the workplace and provide fresh air to workers in the space. Some administration controls include safe work procedures, rotation of tasks to reduce exposure, training, and educating workers about how to use various controls that there are in place. Personal protective equipment for welding includes respirators, eye protection, protective clothing, and gloves. So how do we control metal fume exposure? Typically in workplaces, it's easier to control a hazard at a person, but as we saw on the previous slide, this is the least effective option. Let's talk about some ways we can control welding fume. Controlling fume as close to the source of generation is the most effective control, but this can be the most difficult to achieve. These control options apply for most hazards we encounter in the workplace. There are several types of local exhaust ventilation systems that can be used to reduce welding fume exposure. The first are fume extractors. These devices capture fumes directly at the source before they can disperse into the surrounding air. They come in various forms, including portable units that can be positioned near the welding area and fixed systems integrated into the welding stations. Extractions arms. These are flexible arms attached to fume extraction systems that can be positioned close to the welding process to capture fumes directly. There are also downdraft tables that can be used where welders weld their items on top of tables with built-in ventilation systems that draw fumes downwards away from the welder's breathing zone. Respirators are protecting the person from exposure, so they rely on high efficiency or HEPA particulate filters or powered air purifying respirators can provide additional protection to staff, especially in situations where fume extraction may be less effective or in confined spaces. Ensure that the work area is well ventilated, either through natural means or mechanical ventilation systems, and make sure that welding is designed into the workplace to minimize the dispersion of fumes. Combining LEV systems and appropriate PPE is generally considered the best approach to significantly reduce welding fume exposure and maintain a safer working environment. So let's have a look at local exhaust ventilation. We'll start with LEV type capture hoods. So selecting and installing LEV can be complicated. You'll likely need to engage a professional to help you select the right system. There are many potential pitfalls with LEV. These include poor design, poor installation, and inadequate maintenance of any one component. This will reduce the ability of the system to remove fumes. You'll need to train workers to complete routine daily checks to see if the LEV is operating as it should. Defects must be reported immediately to ensure effectiveness of this control measure. It can be useful to install an airflow indicator such as the manometer to check that the LEV is working properly. The fans, ducts, and hoods will vibrate, so putting in an LEV system will also introduce a source of noise, which will need to be factored into design of any new system. Fitting or retrofitting additional hoods to older systems can significantly reduce the system's effectiveness. In general, positioning the hood should be as close as possible to the work or the source, ideally less than 1 hood diameter away. The welding area should be enclosed as much as possible to avoid drafts that will blow the fumes away from the hood into the workplace. Ensure the hood is the right design for the process and type of fumes, and the welder must not be positioned between the fumes and the hood. You can see a couple of mistakes being made by the operator in the left image. The hood is too far away from the source, and the operator has positioned himself between the hood and the source of the fume, meaning that any fume that the hood is extracting is also going through the operator's breathing zone. On the right, the operator has positioned the hood in a much better position. It's closer to the source of the fume generation, and he's not between the hood and the workpiece. So let's have a quick look at LEV or on torch extraction. So the closer the welding fume extraction is to the point of origin, the more effective the capture of the metal fume. So the benefits of using on torch extraction mean that operators don't have to reposition capture hoods, which can be a big pitfall of the previous system. If the operator isn't motivated to move the capture hood when they move to the next part of the weld, then the control falls over. But if the extraction is always moving with the welder and they don't have to think about it, then it's going to be a lot more effective and take a lot less management to make sure that staff are using the control effectively. So advances in design have led to much more compact and ergonomic extraction units that can be placed on torch. They are integrated much better into welding torches. Some of them you can barely tell now that there is an integrated extraction on the torch head. They're much lighter and less cumbersome to use than previously. And filtration technologies have also improved to reduce the footprint of the filtration system and increase portability. We're seeing increased adoption of these types of systems, which is driving technological advances and reducing overall costs. A respiratory protection. So there are many types of respiratory protection available for welders, from negative pressure half-face respirators to airline respirators. However, powered air purifying respirators, or PAPR, are fast becoming the respirator of choice for welders. They offer several advantages over negative pressure respirators. One, you can seamlessly integrate welding masks into the system. The units draw in air from behind the welder, meaning that the filters last longer due to not being directly in the welding plume. They can provide a cooling effect to the operator due to the airflow across the face, and they don't require fit testing, and facial hair is much less of an issue. If you're using negative pressure respiratory protection, such as the top two examples of a full face and a half face mask on the right-hand side there, they will require face fit testing. Beards and facial hair can reduce the effectiveness of negative pressure respirators, and operators need to meet stringent facial hair requirements and be clean shaven where the respirator seals to the face. So ensure respiratory protection fits well with other PPE. This is a strong requirement for selecting any type of respirator. So you have to make sure that you can integrate all of your PPE, such as hearing protection and welding visors, and that it all works well together. For RPE to be an effective control, many things must happen, including selection of appropriate RPE, medical screening for staff wearing certain types of RPE, training, issue of respirators, fit testing, ensuring RPE is worn when required, maintenance of RPE and replacement of worn parts, and a number of other things. An RPE program should be established to help manage these items, and there should be an administrator or administrators of the program to ensure it runs properly and that all of the items are addressed. Many times we've seen RPE issued to a worker with no other information, and they don't know how to maintain or store it, leading to key components of the respiratory protection failing and reducing the effectiveness down to really none at all. So what's the most effective control? A study by Peter Knott and Associates in Australia titled Welding Fume, a comparison study of industry-used control methods, was published last year and used a controlled environment to test the effectiveness of common controls for welding fume. It should be noted that this study was conducted in a controlled enclosure, and results may differ in real working environments. But they were able to show that powered air purifying respirators were able to reduce operator exposure to welding fume by over 99%. This is a great control to protect the operator, but the study also showed the importance of removing welding fume from the worker environment, as the testing showed that welding fume levels were almost the same 1 meter away from the operator as they were in the breathing zone of the operator when no extraction was used. These findings have implications for workers in the nearby vicinity of the welding, who may not be wearing respiratory protection, and for welders themselves when they remove their welding mask but keep working in the same environment. On-tool extraction was shown to be more effective than LEV capture hoods in the testing, with a reduction in welding fume concentrations by 12 and 9 times respectively compared to no extraction. Both systems were shown to be very effective in reducing welding fume exposure. And the study showed the importance of not just picking one control, such as using a respirator to protect the worker, but also the importance of using a multi-layered control approach. So I'm going to talk about the workplace exposure standards now. So these are guidance values set by WorkSafe New Zealand. These are concentrations either in parts per million, parts per billion, or milligrams per cubic meter, which should mean that most workers can be repeatedly exposed to this concentration without coming to harm. There are a lot of factors that can affect the WES, including synergistic effects, ototoxic effects, sensitizing effects, and many others that we won't go over in depth here. Therefore, you should only apply WES values when you have a good understanding of occupational hygiene. The WES have 3 main types. Time-weighted average, or TWA, is simply an average exposure over an 8-hour working shift. This is designed to cover continuous or frequent intermittent exposures throughout the workday. These will be set to reduce the likelihood of chronic health effects. STEL, or short-term exposure limits, a 15-minute exposure allowed a maximum of 4 times per shift with at least 1 hour gap between exposure events. These protect from acute effects for example, intoxication from ethanol. Ceiling limits. These are not safe to exceed. They protect from acute effects, which will have immediate impact on the health of the worker. For example, chemical asphyxiation from carbon monoxide. New Zealand does not have an exposure standard for whole welding fume anymore since 2022. WorkSafe New Zealand considers whole welding fume exposure to not be sufficient in protecting workers' health. Exposure assessment of welding fume should be based on measurement of known or expected components in the welding fume, which would include metal constituents as well as shielding gases and contaminants produced during combustion of surface coatings. Some metals have respirable workplace exposure standards as well. Different monitoring techniques are required to assess the appropriate fraction. You can see some common metals in welding fume and their exposure standards on the right-hand side of the slide. Note that some of the compounds, such as chromium-6, have particularly low workplace exposure standards, in part due to the seriousness of the illness associated with them and the risk of cancer from relatively low levels of exposure to the substance. And others have both inhalable and respirable workplace exposure standards due to the health effects associated with different particle sizes for these substances. To set workplace exposure standards in New Zealand, WorkSafe reviews scientific data such as hazardous properties, whether it's a carcinogen, corrosive, skin impacts, etc. They look at pharmacokinetics, which is how a substance behaves in the body. And then they look at epidemiological data, which is what we know about how the substance impacts the health of the target species. And it could include animal studies, cohort studies from various groups that have exposure history and looking at the health outcomes experienced by those groups. Then internal and external specialists review the data before going through a question and answer process and putting it out for public consultation. After consultation, a decision is made on the new WES, which is set and published on the WorkSafe website. So workplace exposure assessment can be done to look at the controls associated with welding and to look at what levels that workers may be exposed to. So we can undertake qualitative assessments of workplaces to help you identify and risk assess your work processes, which can include welding. We can undertake exposure monitoring to quantify your metal fume exposure. Without appropriate controls in place, we often see welding fume exposures above the workplace exposure standard. But after implementation of good quality controls, then the level of welding fume can be reduced to below the workplace exposure standards. We can also advise on the types of controls that will best suit your particular situation. And we can fit test respirators to ensure that they're appropriate fit for staff and help out with respiratory protection programs if they're needed. Key takeaway messages from this webinar: welding and metal fumes are common in New Zealand workplaces. Metal fumes are known to cause cancer and are hazardous to the respiratory system. Lots of workers have exposure to metal fumes above the current workplace exposure standards. There are controls available that are able to significantly reduce worker exposure. Combination of controls is likely required to protect workers. Whatever controls you use, it is important to train your workers and monitor their effectiveness. Thank you very much for your attention. Please send any questions through to info@chemsafety.co.nz and we'll do our best to get back to you.